So now I'm gonna solve this problem. We have Leetcode 109 convert sorted list to binary search tree. So we have as an input linked list that's sorted, and we need to convert it to a binary tree. So as you might notice, here it's already sorted. That means that if I split this linked list into two parts, so we have 5 elements. I have a left subtree and right subtree nodes, and the parent is equal to 0. And I can do that recursively for the left and for the right subtree. So I can split it in two. Let's say we have right like root element like parent element -3, and then it's either we have element as a child or no as a null, and the same for the right subtree. If I just go through this tree and do in order traversal, so I go -10, -3, nothing on right, then 0, then I go 5, then 9, and it's gonna be exactly the linked list. So my idea here is to do in order traversal kind of, and maintain the head of the list, or like current cursor for the list, and do this left right pointer, and whenever like left equals right, I'm gonna kind of have interval for the subtree, and yeah, I need basically to half it every time I go to the child. So for the as a first number, as a step number 1, I need to calculate the number of elements into this linked list. Let's say we have n equals 0, 1, and let's say we have a list node current equals head, and then while current not equals null, we do current equals current next, and then it'll do that n plus plus. So now we have number of nodes into the linked list and also in the binary tree. So I want to do this DFS, and I want to pass a left index and the right index, and the right index is going to be for the root element going to be n-1, and I also want to have a head, but I want to modify that in place. So I want to pass the new list node, and that's going to be just head here. And this is gonna return the root element, return tree node. So the DFS function, the DFS function gonna have private tree node DFS, and then we're gonna have a left, gonna have right pointer, and we're gonna have a list node array for the head, list head. Let's call it list head. So what we're gonna do here, so if left equals right, then I'm gonna do the following. I'm gonna create new tree node, and let's assume we have tree node equals new tree node. And then what I wanna do next is I wanna get the list head val, and I want to push the list head, let's say 0 val. List head 0 equals list head 0 dot next. And I want to return the list, return node. Else, if left not equal right, I want to do and find the middle point. Middle equals left plus right minus left over 2. And what I want to do is create 3 node middle node equals new 3 node, and then middle node dot left equals DFS left gonna be the same, and right gonna be middle minus 1. I'd say if left greater than right, then we're gonna have return null. And here middle node left equal DFS L minus 1, and then I'm gonna push list head, and then middle node dot val equals list head 0 dot val. Then we're gonna push the next element, and middle node dot right equals DFS m plus 1, and then right, and then list head. And what I do the next, I return this, return middle head, middle node. That's it. Let me quickly check this one. Okay. Oh, there is edge element if. Oh, that's interesting. Yeah, that's nice. So initially, if there are like 0 elements, we're gonna push 0 and n minus 1. So gonna be 0 and minus 1, and this gonna be true, and we're gonna just return null. If there is 1 element, what's gonna happen? So gonna push, gonna call DFS for 0 and 0, and if left equals right, we're gonna create 0 equals 0, we're gonna create list node head with head value. We're gonna put the null into list head, and then we're gonna return it back. Let's say we have like two nodes in our list. I'm gonna put call DFS with 0 and 1, and then if this is gonna be not gonna be executed, and then we're gonna call DFS. So call DFS for 0, 1, and then middle in this case gonna be 0 plus r minus plus 0. So we're gonna call left for the DFS. Left gonna be 0, m minus 1, minus 1. So in this case, left middle left are gonna be null. Then gonna create node value, then list head. So the middle element gonna receive here middle node value of the current head. Let's say we have like 10 and then 11. So the middle will receive 10. And then on the right, middle right, we're gonna call DFS, and then it's gonna be middle 0 plus 1 1, and then right 1, and then gonna call it left equals right. And we're gonna get the next list head here, and gonna be 11, and then we're gonna push the null into list head here. So this one gonna have list right 3 node, and the value gonna be 11. Yeah, I'm gonna return this middle 10 middle 3 node back. So that was for the 3 or like list with the length of 2, and the same gonna happen for the length of 3 and 4 and so on and so forth. The idea here, the main idea here, I assume we push the ranges into DFS and we split it into 2, and we push the left part and create like left subtree, and we push the right part and create a right subtree. And whenever left is greater than right, we return null. When it's like equal, it means it's child node. And we create a node and we push it back up. And for parent nodes, we create them here, and again we push the list head and we return the parent node. So if I run it, and even if I submit it, that should be successful. Let's check the memory. Memory actually not that good. I wonder why. What's the best memory here? So they have a kind of interesting solution with the head 1, head 2. Let's check out. So it seems like they are not calling DFS, and they have like fast and slow pointer. So they try to find the middle element here. Hmm. But the time complexity, every time they gonna do this move with slow and fast pointer in order to figure out what's the middle one. So for this one, time complexity would be like of n, when n is number of lists, number of like nodes in a list, and we do that 2 times, go through the list, like when we do while, count the number of elements in the list, and then when we do this DFS, and so the time complexity gonna be O of n, space complexity gonna be O of 1 actually, but because we do this splitting and we're gonna call this function recursively, so like the maximum call stack gonna be, so it's gonna be log n. Yeah, because a call stack, in a call stack we create these variables and we split all our n's by half, like here, every time. So generally the depth of the call stack gonna be log of n maximum. But here, let me check. Let me check the solution. Like this one. With two heads, what they do here? They do while head. Yeah, head 1 just 1 next, and head 2 is a fast pointer. Head 2 is a fast pointer here. And they call sub function. So it's also gonna be log n here, but multiplied by every time we need to go till the end. So we split it there, and we need, okay, so we need to split it again so that next time when we call it for the subtree, it's gonna end like right in the middle. So for the middle element, like previous, it's previous to the middle element, we push the, like, put the previous next equal null, and we break the chain here. Okay, let me try to execute this one and see if it's, what's the time complexity here. So every time on log n, so for the first iteration gonna be, we need to go through the first iteration gonna be n time complexity. The second iteration gonna be so we have n over 2 and then n over 2 for the two parts, and then for the third one level n over 4, n over 4, and then n over 4, and then n over 4, and then so for the every we have n multiplied by log n. So the time complexity here, interesting, and the space yep, the space complexity, it's again gonna be like log n, because we need to go deep on every level and we don't create any kind of arrays on every, like it's on every call for the sorted list to BST. So it's gonna be time gonna should be n log n, and the space should be log n. Check that one. Okay. Okay, that's it. I'm gonna wrap up.